It's sad to think we're not gonna make it.
3.6 Probability involving permutations and combinations. Another tough section. So we did all this stuff with permutations and combinations in the last chapter, and now we're going to use that same sort of knowledge to answer some pretty difficult probability questions. So we'll do 4 or 5 of them here. Jamal, Ethan, and Alberto are competing with 7 other boys to be on their school's cross-country team. All the boys have an equal chance of winning the race. Determine the probability that Jamal, Ethan, and Alberto will place first, second, and third in any order. So first thing you have to do is you have to figure out, remember with probability, for all the questions we do today, we need to have the number of favorable outcomes, and we're going to divide that by the number of total outcomes. So in this question, favorable outcomes is Jamal, Ethan, and Alberto being in first, second, and third place. So if you think of it, first, second, third place, how many of the boys could be in first place? 3. How many could then be in second place? Well, there's only 2 because you've picked one for first place, so 2 could be in here, 1 could be in here. And of course, with the fundamental counting principle, you multiply those together and you get 6. Another way you could think of it is you have 3 boys and you want to take those 3 distinct objects, if you will, and order them in first, second, and third place. How many ways can you do that? So it's 3p3, and what we learned before is that's the same as 3 factorial, and 3 factorial equals 6. Anyway, it doesn't matter exactly how you do it, as long as you understand the number of favorable outcomes. There's 6 of them. There's 6 favorable outcomes. Now, how many total outcomes are there? Well, the number of total outcomes is the number of ways to take your how many boys do we have here? 10 boys, because we have these 3 plus 7 more. So we're going to take our 10 boys, and we're going to see how many different ways could we have ordered any 3 of them in first, second, and third place. In other words, order matters, so it's a permutation, and you want to take those 10 distinct objects, the 10 boys, and see how many ways there are to put them in order first, second, and third. So that's 10p3. And if you use a calculator or whichever way you want to do it, you'll find that that equals 720. If you don't like the permutations, I know a lot of people, myself included, aren't totally crazy about permutations. I like combinations, but permutations confuse me sometimes. You could think of it this way. In first place, if you think of all the boys, how many boys could have been in first place? 10. How many boys could have been second place? Well, you're down to 9 because we chose one to go in first place, and then 8 here, and if you multiply those together, you get 720. So basically, to get the probability, you're taking 6, the number of favorable outcomes, you divide by 720, the total number of outcomes. If you divide top and bottom by 6, you get 1 over 120, and that's our answer. So Bo hosts a morning radio show in Saskatoon, and Bo's a man, by the way. To advertise his show, he's holding a contest at a local mall. He spells out Saskatchewan with letter tiles. Then he turns the tiles face down and mixes them up. He asks Sally to arrange the tiles in a row and turn them face up. If the row of tiles spells Saskatchewan, just like it did here, Sally will win a new car. Determine the probability that Sally will win the car. Come on, Bo. I mean, even without doing the question, I can tell this is so unlikely. If you mixed up all these letters and then without looking put them in an order, it's just not going to happen. This is not common at all. Boo to Bo, I say. So, same thing, we want to figure out the number of favorable outcomes. Well, the number of favorable outcomes refers to the number of ways to spell Saskatchewan. Saskatchewan. Well, think about this here. What would your English teacher say about this? If you went to your English teacher and said, hey, how many ways are there to spell Saskatchewan? They would say there is only one way. There's one way to spell Saskatchewan. Here it is. That's how you spell Saskatchewan. Now, the next thing we want to do is figure out the total number of ways to jumble up these letters, right? When Sally puts all the letters in order, how many different words words with quotations, right? Because most of them aren't really words. How many total ways are there to arrange the letters, we'll say? Remembering that we do have some repetition here. So what we do is we count up all the letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it'd be 12 factorial. However, as I said, we have some repetition. What repeats? We have S, S, that's it, and we have A, and that's it. So we have 2 S's, 3 A's. Do you remember what that means? It means the number of ways to rearrange the S's is 2 factorial. The number of ways to rearrange the 3 A's is 3 factorial. If you figure this out, you will have the total number of ways to arrange these letters and taking into account the fact that some of the elements are the same as each other. So if you do that, you will end up with the answer 39,916,800. No idea why the big space here. So the final answer, the probability that Sally gets it right, is 1 in 39,916,800. And just to give you a sense here, the probability of winning the Lotto 649 is about 1 in 13 million or something. So this is 3 times more unlikely. As I said before, Bo is a cheapskate. This one's hard. There are 18 bikes in Marnie's spinning class. The bikes are arranged in 3 rows with 6 bikes in each row. So maybe I'll start by just drawing that. So in the first row, there's 6 bikes. 1, 2, 3, 4, 5, 6. In the second row, 6 bikes. 6. In the third row, 6 bikes. 1, 2, 3, 4, 5, 6. And Marnie's going to class with Allison, Brett, Carol, Doug, Eric, and Fletcher. Isn't that cool? A, B, C, D, E, F. I'm sure that's how Marnie picks her friends. Maybe Gary or Giovanna will be her next friend. So anyway, Marnie and her friends go to the gym, but they call ahead to reserve a bike. And they want to be in the same row. I mean, come on, people. Don't be so uptight. But they want to be in the same row, and they can't request a specific bike, so it has to, just get lucky. Determine the probability that all 6 friends will be in the same row, and not only that, Allison and Franco have to be at either end. I have no idea why Allison and Franco don't get along, or they like each other too much and can't keep their hands off each other. I have no idea, but Allison and Franco have to be at the ends. So let's put Allison and Franco in the first row. Allison, Franco. So one thing we have to consider is, remember, who we're going to put in these 4 spots here are Brett, Carol, Doug, Erica, and Marnie. So what you have is 4 people, and we're putting them in an order, right? Putting Marnie here is different than putting Marnie there, so it's a permutation, and we want to order all 4 of them. Or if you want, another way you could think of that, because this is what this means, is it's 4 factorial. Because in the first spot you could put any of the 4 people, and then we're down to 3, down to 2, down to 1. So 4 factorial will take care of how many ways to arrange the people in the first row. But here's the thing, there's not just this row they could be in, they could also have been in this row, or they could also have been in this row. So this, just to hopefully make this somewhat clear, this is the number of ways to arrange them in one row. Arrange friends in one row, I'll put. But we also have to put the number 3 here. We're going to multiply by 3 because there's 3 possible rows they could have been in. So this is 3 rows. Now we got to fill the other spots in here too, is with the other people. So there's 18 bikes total. These 6 friends fill up here. So how many people are we left with? 12. How many people go in this one? 12. How many in this one? 11. How many in this one? 10. So another way you could think of it is you're going to have 12 other people. You're going to order them because it depends which bike they pick makes a difference. So it's a permutation, and you're ordering all 12, and that means the same as 12 factorial. So this is arranging all the other people, the non-friends. Oh, and there's one thing I've forgotten. We also have A and F here, but all it says is that Allison and Franco are at either end. I have an A here and F here. Could be the other way around, right? It could have A here and F there. So we also need to do a 2p2, which is the same as 2 factorial. And again, that's because you could put either one of those guys, A or F here, and since you have 2 here, 2 to choose from here, you'd only have 1 here, so 2 times 1. This is the number of ways to arrange A and F. So believe it or not, when you want to know how many different favorable outcomes there are, you need to multiply 2 factorial times 4 factorial times 12 factorial, and you also need to multiply it by 3. I'll put 3 up front. 3 times 2 factorial times 4 factorial times 12 factorial. Now on the bottom what we need to put is the total number of ways to arrange 18 people on these bikes. So in other words, what you want to do is you want to take 18 people and you want to arrange them, and order matters, and you want to arrange all 18. So it's 18p18, or if you want, the other way you could write that is 18 factorial. So what the heck, I'll write that 3 times 2 factorial times 4 factorial times 12 factorial all over 18 factorial, and if you do all that, you're going to get, it simplifies to 1 over 92,820. Good luck, guys. I don't think you're going to be spinning together. Okay, the last question has to do with playing cards. Remember, there's 52 playing cards in a standard deck. So 4 friends are playing cards, and you want to know what the probability is that one of the players will get 4 aces in a 13 card hand. Let's do the total first, okay? First of all, when you play cards, does order matter? No, it doesn't matter which order you get dealt the cards. So this is going to be a combination. And for the total number of outcomes, you have 52 cards, and it's a hand of 13. So what you're going to do is you're going to choose 13. That'll give you the total number of outcomes. Now, we want a hand with 4 aces in it. So how many aces are there in a standard deck? 4. How many of them do we want to choose? All 4. So 4 choose 4. By the way, that equals 1. Times, what else do we need? Well, we need 9 more cards. 9 out of how many? Well, when you take 4 away from the 52, you're left with 48 other cards, and you want to choose 9 of those cards. Now, there's one other thing we have to do as well. This is the probability that a single person gets the 4 aces in a 13 card hand. But there's 4 people sitting around the table. So there's actually 4 chances for this to happen. So you need to multiply all of this times 14. Because it could be the first person, second person, the third person, or the fourth person that this happens to. So if you do all that, you will end up with the answer, when you simplify and everything, 44 over 4,165. Try it for yourself if you want. You could make it a decimal, 0.011. You could even make it a percentage. Move the decimal over 2 spots, you get 1.1%. There's a 1.1% chance that one of the players will get 4 aces in a 13 card hand. Not possible for 2 of them to get 4 aces, by the way, right? It's only possible for one of them to get 4 aces. And the reason for that is because there's only 4 aces in the deck. Last one, what's the probability that one of the players will not be dealt a face card or an ace in a 13 card hand? So it's actually pretty similar, like the same sort of strategy as the last one. Total number of outcomes, well, you're starting with 52 cards, and order doesn't matter, so it's a combination, and it's a 13 card hand. Now, what's the probability that one of the players will not be dealt a face card? Remember, face cards, we've done this so many times, are Jack, Queen, and King. And we have 4 suits, so times 4, 3 cards times 4 is 12 face cards. Or an ace. How many aces are there? 4. So we have 12 face cards. We have 4 aces, so that's 16 total cards that we don't want to have. So in other words, we want 16, these 16 cards right here, how many do we want to choose of those? None. We don't want any of those. 16 choose 0. If you remember, 16 choose 0 equals 1. Times, how many cards are left? Well, we started with 52, but we're not considering these 16. We don't want those 16. That leaves us with 36 cards. How many of those do we have to choose? We've got to pick all 13 of the cards from there, right? We don't want any of the 13 to come from these 16 cards. We pick 0 of those. We want all 13 cards in the hand to come from these 36. So here's our answer. Except, once again, we have 4 shots at it. There's card player number 1, card player number 2, card player number 3, card player number 4. So it's like this. If you do all that, you will end up with 0.015, which translates to 1.5%. Not very likely, but it's not outrageous. You play 60 to 70 times and probability states that it might happen, it could happen, it should happen even. Alright, there you go. We're finished probability. Good for you. That's a tough chapter. Onwards.
the first.